Hello friends, Mr. Burrell here. We're in our graphical analysis unit right now. Today we've been talking about how to use the first and second derivative to analyze some characteristics about a function, where it's increasing, decreasing, where it's concave up, where it's concave down, etc., 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 things like that. Today we're going to answer very similar questions to that. But we're going to be doing so using graphs instead of functions. So today we're going to be focusing on reading the graph of a derivative and answering some of those questions about the characteristics of a function. Okay. So first of all, let's ask ourselves the question, what does the graph of the derivative of a function tell us? Well, if we rewind, remember the derivative tells us about the behavior of the graph, right? If I know that the derivative is positive on a given interval, I know that the original function is increasing. If I know the derivative of a function is negative, I know that that function is decreasing, etc., etc. We were able to use that information to find maximums, minimums. When we found the second derivative, we were able to find additional information like concavity, points of inflection, etc. We could do that all kind of algebraically using derivatives of functions. Okay, actually finding derivatives of functions, we could answer a lot of those questions. Okay. However, on the AP exam, okay, many times they don't just give us an equation of a function to work with. Instead, they'll give us the graph of the derivative of a function and ask us a bunch of those same questions, okay? From this graph of the derivative, we're not going to be able to create the original function, okay, but we'll still need to answer all of these questions. Where is that original function increasing, decreasing, concave up, concave down, etc. Okay, so let's take a look at a graph. Let's say this graph right here is the derivative of f of x. Okay, we have some function f of x. I don't know what that function looks like. I don't need to know what that function looks like. But this is the graph of the derivative of that function. Okay, so we're going to use this graph to describe on the interval from 0 to 7 here, where the graph is given, we're going to describe many of the behaviors of this original function, f of x. Okay? So first of all, where is f of x increasing? Well, let's remind ourselves, back at the beginning of this unit, how did we determine where f of x was increasing? Well, I had to find the derivative of f of x, and I had to see where the derivative of f of x was positive, right? That's how I determined where f of x was increasing, where its derivative was positive. Well, on this graph, let's analyze, where is this function, which is the derivative, positive, okay? Well, note that wherever this function is positive, that's where the graph is going to be above the x-axis, okay? So this section right here is where f prime of x is positive, because this is the graph of f prime of x, right? That's where f prime of x is positive. So that's where f of x is going to be increasing. Okay, so here we would say something like this function is increasing on the interval from 2 to 5, and my justification would be because, now I would say because f prime of x is positive on that interval. Okay, that would be my answer with my justification. How do I know f of x is increasing on the interval from 2 to 5? Because f prime of x, the derivative, is positive on that interval. Okay. So vice versa, if we want to know where a function is decreasing, I would need to know where the derivative of that function is negative. In this case, since this is the derivative of f of x, where the derivative is negative is where this graph will be below the x-axis. Let me move my face out of the way. So I'm going to be looking right here and right here. So I would say something to the effect of f of x would be decreasing from 0 to 2. And again, whoops, from 5 to 7, okay? So that's where f of x would be decreasing because, and I would say because f prime of x is negative on those intervals, okay? So that's how we were able to determine if a function was decreasing, is where its derivative was negative. On the graph, I can see that the derivative is negative from 0 to 2 and from 5 to 7, okay? So we can determine from the derivative where a function is increasing, where it's decreasing. Now let's talk about how I can determine where a function has a relative maximum. Okay. Well, reminder, again from the beginning of this unit, I can find a relative maximum of a function wherever the derivative changes from positive values to negative values. Back at the beginning of this unit, we had like a number line. We found our critical points, whatever they were. and say this is where my derivative was positive, this is where it was negative, this is where it was positive. At this point right here where the derivative changed from positive to negative, I knew I had a relative maximum. Okay. Well, the graph itself here, notice this graph is kind of like the number line that we created at the beginning of this unit. Okay. I just need to see where the graph of this derivative changes from positive to negative. Okay. So you'll see my derivative is negative, and then it changes to positive right here. And then it changes from positive back to negative right here. So where does my derivative graph cross the x-axis going from positive to negative? Well, at x equals 5. Okay? At x equals 5. And my justification would be because f prime of x changes from positive to negative. Okay? From positive to negative. I'm going to abbreviate there. That's how I can tell where I have a relative maximum. And then in like fashion, where if I want to find out where f of x has a relative minimum, vice versa. I need to find where f prime of x, this being f prime of x, changes from negative to positive. Okay, so right here at x equals 2, my derivative changes from negative to positive. So x equals 2 is where I'm going to have a relative minimum because the derivative changes from negative to positive there. Okay, you could maybe visualize my original function. If I wanted to go and graph the original function, I'm decreasing from 0 to 2 because my derivative is negative. I'm increasing to the right of 2 because my derivative is positive, and I have a minimum at x equals 2. So I don't know, maybe my graph looks something like that in this range right here, where I'm decreasing, I have a minimum, and then I'm increasing. I don't know exactly what the original function looks like. I don't need to. I don't have to. I'm not going to. That's not going to be beneficial to me. But I can still determine where it's increasing, decreasing, and where, in this case, I have maximums and minimums. Okay? All right, so far so good. I don't think that part is terribly difficult, okay? It's not incredibly challenging doing these things by themselves, finding where it's increasing, decreasing, etc., because it's very similar to what we saw before. Okay, it's just those intervals where the graph or where the derivative is positive and negative is given to me on the picture of this graph. Okay, but of course, there's more. It's going to get more difficult. So let's go over what we're going to be looking for next. We've talked about how to determine where a function is increasing and decreasing, where I have maximums and minimums. But that's not all the questions we've answered so far. Okay, let's see some of the other things that we might be asked to find. Okay, remember when we were talking about the second derivative test, we needed to determine where a function was concave up, where a function was concave down, and where I had a point of inflection. Okay? Oh, whoops. In order to do that in the last lesson, we used the second derivative. I had to determine if the second derivative was positive. If that was the case, then my original function was concave up. If I found intervals where the second derivative was negative, those were intervals where the function was concave down, and where f double prime of x was equal to 0, slash when the concavity changed. If the concavity changed from positive to negative or negative to positive, etc., I had a point of inflection. Okay? So this is going to get a little bit trickier because I don't have the graph of the second derivative. Okay? Nor will we won't be expected to draw the graph of the second derivative. I'm still only going to be able to use the first derivative graph. So let's talk about what we can look for on the first derivative graph to help us to identify some of the things we answered with the second derivative previous to now. Okay? Let's look at some examples. Okay? So first of all, I don't want you to look at that. I want to draw you a picture. Okay? So if I have a function, okay, and I need to figure out where it's increasing or decreasing, I find the first derivative, right? If I needed to find where it was concave up or concave down, I found the second derivative. Okay? Well, if all I have is the first derivative, okay, if all I have is the first derivative and I need to know, say, where the second derivative is positive, okay, if I want to find where the function is concave up, I need to know where the second derivative is positive. Well, the second derivative is the derivative of f prime of x, right? F double prime of x is just the derivative of f prime of x. Well, if I need this derivative to be positive, if this derivative is going to be positive, that means going one step back, this function right here is going to be increasing. Okay, if I want the second derivative to be positive, that means the first derivative is going to be increasing. If I want to know where the second derivative is negative, that means the first derivative is going to be decreasing. Because when some function, call it the derivative here, if f prime of x is decreasing, that means its derivative is going to be negative. So when f prime of x is decreasing, its derivative, or the second derivative, is going to be negative. Okay, so let's take a look at what that means for us. Okay, so if I have the graph of f prime of x and I need to determine where my original function f of x is concave up, I'm going to find on what intervals f prime of x is increasing. Because if f prime is increasing, its derivative f double prime will be positive. And when f double prime is positive, that means my function is concave up. Okay? So when f prime is increasing, f is concave up. Okay? Did we already do? Yep, okay. If I need to know where my function has a point of inflection, okay, I need to know where the concavity changes. I need to know where the second derivative changes sign. Well, where the second derivative changes from positive to negative or negative to positive, that's going to be where the first derivative changes from increasing to decreasing or decreasing to increasing. So if I'm looking at f prime and f prime changes from increasing to decreasing or decreasing to increasing, that's where I have a point of inflection. Okay? So if I'm given f prime, to find a point of inflection, I look where f prime changes from increasing to decreasing or decreasing to increasing. Let's see. Whoop, okay, here we go. And lastly, if I need to determine where a function is concave down, I need to look for where f prime, the graph of f prime, is decreasing. Because if f prime is decreasing, its derivative will be negative, meaning the second derivative would be negative. And when the second derivative is negative, that means my original function is concave down. So in order to determine where a function is concave down, the first derivative must be decreasing. Okay? All right. Now let's go back to our graph of f prime, the graph of the derivative here. Let's answer some questions. So here it says, on what intervals is f of x concave up? Okay. Well, if f of x needs to be concave up, that means f prime of x needs to be increasing. Well, where is f prime of x increasing? From here to here, and from here to here. So f of x is concave up from 0 to, oh gosh, what is that? Should we call that 4? We're just gonna say that's 4. We're just gonna say that's 4 for ease of computation here. From 0 to 4 and from 6 to 8, because f prime of x is increasing on those intervals. Okay? On what intervals is f of x concave down? Well, I need to look for where f prime of x is decreasing. That's going to be, call it from 4 to 6. So on the interval from 4 to 6, f of x is concave down because f prime of x is decreasing on that interval. Okay? Now, where do I have points of inflection? Well, points of inflection happen wherever concavity changes. Concavity changes when the derivative graph here changes from increasing to decreasing or increasing to decreasing. So right here and right here, you could visualize that as relative maximums and minimums. So points of inflection happen at x equals 4 and x equals 6 because f prime changes from, and I would say from decreasing to increasing or increasing to decreasing or something like that. Okay? That's where points of inflection happen. Looking at the derivative graph, again, this is the derivative graph. Points of inflection happen when the first derivative changes from increasing to decreasing or decreasing to increasing. Okay. So one important thing to note, when we answer these questions, we have to reference the graph we are given. So you'll notice all my justifications. I've said, this is true, this function is increasing or decreasing or concave up or concave down because, and then I'll reference the graph that was given, f prime of x. Okay? we never want to reference something that's happening on f of x or f double prime of x because that's not the information that the problem gave us. The problem gave us the graph of the first derivative, f prime of x. So all of my justifications would need to be referencing the first derivative graph. Okay? So the last couple things we need to talk about, what if I combine multiple characteristics together, right? So let's say given the graph of f prime of x, here's the graph of f prime of x shown to the right on the interval from 0 to 10. On what intervals is f of x both increasing and concave up? Okay, so now I'm answering two questions. I have a different graph here. So first of all, let's determine where f of x would be increasing. Well, f of x is increasing when f prime of x is positive. If f is going to be increasing, its derivative is positive. Okay, so if this is the derivative graph, my derivative is positive right here and right here. This is where f of x is increasing because f prime of x is positive, okay? But I don't just want the intervals where f of x is increasing. I want to know the intervals where f of x is concave up. Well, in order for f of x to be concave up, f prime of x needs to be increasing. Because if f prime of x is increasing, its derivative f double prime would be positive. But again, I want to answer all these questions referencing the derivative graph, which is the graph I'm given, okay? So I need to know where f prime of x is increasing. Let me change colors here. F prime of x is increasing right here, right here, right here, okay? So basically, I want the intervals where I have drawn on my graph in purple and in red, where f prime of x is positive and increasing. So right here and right here. Okay, so I would say, on what intervals is f of x both increasing and concave up? From, oh, I don't want the purple, I want the red back. So it's going to be from 0 to, again, let's just call that 2. From 0 to 2, and from 6 to 9. And then I would say because, and then here's my justification. F prime of x is greater than 0. F prime of x is increasing on those intervals. Okay? So f of x is increasing and concave up on the interval from 0 to 2 and from 6 to 9 because f prime is positive and f prime is increasing on those intervals. Okay? Okay, what if I want to know where f of x is decreasing and concave down? Well, for f of x to be decreasing, f prime of x has to be negative. That's going to be right here. And then in order for f of x to be concave down, f prime of x has to be decreasing. Well, I'm decreasing. Let me change colors again. F prime here, again, this is the graph of f prime, is decreasing right here. Then over here, this kind of got cut off over here. So the only place where both of those things is happening is from 3 to, we'll call that 4.5, okay? So from 3 to 4.5, f of x is decreasing and concave down on the interval from 3 to 4.5 because these things are true on that interval. Okay? Alright, let me change this back to red. Let's look at one more. At what x value, this one's a little bit different, at what x value is f of x both decreasing and a point of inflection? Well, for f of x to have a point of inflection, remember f prime had to be changing from increasing to decreasing or vice versa. Okay? Well, right here, and right here looks like f prime, because again, this is the graph of f prime, is changing from increasing to decreasing or decreasing to increasing, okay? But it doesn't just want where f of x has a point of inflection, but it wants to know where f of x is decreasing. Well, f of x is decreasing where f prime of x is negative. Well, here's where f prime of x is negative. So the x value, the point where f of x is both decreasing and a point of inflection, is right here. So we call it 4.5 at x equals 4.5 because of these things right here. There's my justification. It's in an interval where the derivative is negative and f prime of x changes from increasing, or in this case, it changes from decreasing to increasing there. Okay? So that is a really good example of the type of graphical analysis question you might be asked on the actual AP exam. They'll give you a derivative graph, the graph of the derivative, and ask you a bunch of these types of questions relating to increasing, decreasing, concavity, critical points, points of inflection, etc., etc. So I hope that was helpful. Please let me know if you have any questions.